Welcome everyone. I prepared a short keynote about hidden gems in Swift. These are, in my opinion, some rarely discussed topics, which, despite their unpopularity, are very useful and interesting. So, my name is Adrian Kashivskyy. I am an iOS developer at NetGuru, but secretly I've been working as iOS developer for like 6 years now. You may find me on Twitter at Kashivskyy or on our mobile Warsaw Slack at just AK, highlighted in yellow. So, this evening I want to talk about 5 things: literal convertibles, string interpolation, pattern matching, reflection, and Objective-C bridging. So, how many of you are iOS developers here? Oh, majority, yeah. And how many of you have worked both in Objective-C and in Swift in some commercial or non-commercial projects? That's a lot. Okay, so the last topic will be quite interesting to you. So, without further ado, let's dig into literal convertibles. One more thing, the Swift icon with the version number represents the version that introduced a feature that is currently on screen. So, let's dig into it. Let's imagine we have a regular expression structure in Swift. It has a pattern property and initializer, and we want to check whether the user entered a correct email address. We instantiate our regular expression type with the pattern colon, and yeah, that's okay, but imagine that you have a big form. You're developing a Mac application, you have like 50 fields, and each of them has their own regex, and it's quite difficult. Oh, no, it's not difficult. It violates the don't repeat yourself rule to type regular expression parenthesis pattern colon every single time for every single regular expression. So it would be nice to just instantiate a regular expression from bare string literal in Swift. So it's as easy as implementing a string literal convertible protocol. It exists since Swift 1.0. It has a type alias, which obviously you will be defining as string, and a non-failing initializer. And this is the important note that this initializer cannot fail. It can fail if you raise a fatal error inside, but it's not a failing initializer. Every type that you instantiate from a literal must succeed. So, string literal convertible is a special protocol from all the convertibles because it inherits from 2 other protocols. I won't read them, they are at the bottom of the screen. And I had no space to fit it into the slide, but you need to implement them as well, and it's just another type alias and initializer for each of them. So the full code examples will be available at my repository with the talk when the talk is over. So in Swift, there are all kinds of literals. We have an array literal that is implemented by set, for example. There is a Boolean literal, a dictionary, floating type, a nil literal that is implemented, of course, by optional and by selector and pointer as well. Not only pointer, but unsafe, mutable pointers, all kinds of pointers implement the nil literal convertible, which represent the null, the C null value. There is a literal for integer and for string, which is implemented by selector, for example, and that's why you can use strings as selectors in Swift. This is not some LLVM magic, it's just a protocol. So that was all about string the literal convertibles, and now let me talk a little bit, just 2 slides, about string interpolation. So our task here is to use the byte, the type in the byte enum, and to include it in a string for some weird reason. But interpolated string in this case prints just literally byte.0. And our UX designer said it's not possible, it's not acceptable, we need to print 0 or 1, the literal number. So that's what string interpolation convertible protocol is for. And keep in mind that it differs from a string literal convertible in terms of where you declare conformance. You don't declare it on the byte, you have to extend the string type to implement it. So in our case, we need to add one initializer to string, init with string interpolation segment, specifying the type as byte, and then initializing the self from the raw value of byte. And the result of this is the correct value of 0 at the bottom of the screen. Okay, that was very quick about string interpolation. Now I would like to focus on pattern matching. So what is the pattern? Before I show you any code, the patterns in Swift are enumeration cases. So every time you type like case.none, case ns.json writing option .pretty printed, these are patterns in Swift. Single equatable values, and by equatable I mean conforming to the equatable protocol. So any type of ints, literal floating types, ints, and strings, for example. Ranges and intervals are also patterns in Swift. And value bindings are also patterns. By value bindings, I mean let x equal something and and var x equals something. So I didn't make it up. This is actually described as value binding in the Swift documentation. This is not variable declaration. This is not, you don't declare a value, you bind a value in Swift. And also typecasts, S typecast, because is typecasts are not patterns in Swift. So any types of S typecast, so S question mark, S exclamation mark, and bar X, S are typecasts in Swift. So these 5 things, the first 5 things, are implemented by Swift standard library, but as Shia LaBeouf said, it's not animating. Cannot just crash on El Capitan. Okay. Nothing is impossible. You can implement your own patterns as well. It crashed. Oh my god. Sorry, technical difficulties. You can implement your own patterns in Swift by overloading the tilde equals operator. This is an infix operator between 2 operands, and you just need to return a boolean whether the right value matches the left value. So we can implement it for our own regex type, as I showed before, or you can implement it for your types in your programs, whatever you like. Last but not least, tuples of everything above are also patterns. So tuples of patterns are patterns. Where do we use them? So we use patterns, of course, in switch statements. Every time we type case 0, colon, it's a pattern. We use patterns in if-let bindings. We use patterns in for-in loops. So every time you type for x in array, you actually bind the value x and pattern match it. And we also, new to Swift 2.0, we use pattern matching in catch statements as well. So basically, basic stuff. Everybody wrote this code before. A simple case, we have a point. We pattern match it to 0, 0, and if it's at origin, we print origin, or otherwise we print this is an arbitrary point. Everybody wrote this kind of code before. The Swift introduced value bindings and where clauses in cases. So that's something new that wasn't present in Objective-C. And here's where the where clauses kick in. The evaluating condition after the where is actually, during the evaluation, we are absolutely sure that x and y values are already bound. This is very important. I will come back to this in a couple of slides. But in this example, we basically bind x and y and checked whether x equals y. This eliminates an additional if inside our case. So it's just a matter of clearer syntax. But by using where and not ifs in cases, the compiler can actually optimize your code more. So I advise you to use these where clauses, not the nested if statements. If let where, the feature introduced in Swift 1.2. And why, you might ask, why do you need an additional condition inside if itself is a conditional statement? So actually, if let is not a conditional statement, it's a pattern matching statement. And it performs no checking inside between if and where. So it just matches the value or doesn't match the value. And in order to check whether the matched value passes our test, we need to include a where clause inside the if. So in this example, we have an optional point, and first of all, we bind the value of optional point, we unwrap it, we ignore the x value, just leaving the y. And by the time y is greater than 0 is evaluated, we are absolutely sure that y is non-optional because the binding succeeded already. So there is no question mark, no exclamation mark here. Y is non-optional when evaluating the where statement. So in this case, we are checking whether the point is above the x-axis. For in where, the next pattern matching statement introduced in Swift 1.2. This is another place when Apple allowed us to use a where statement. And now imagine you have an array of points, some arbitrary points, and you want to print only those that are in the first quadrant, so in the top right of the coordinate space. In our for in loop, you bind the x value and the y value for each element in points, and then perform an additional check whether the x and y are greater than 0. If so, print that these are in the first quadrant. So as always, we can do this by nesting an if statement in each for loop, in each for invocation, but this allows, as I said, the compiler to optimize your code, and it's just clearer. So, new stuff. Swift 2.0. Enough digging in history. So in our task in this example is to check whether the point is on screen. We have a point, we get the width and height of our screen by asking UI screen. And then traditionally, we would need to write 4 conditions. If x is greater than 0 and if x is less than width. If y is greater than 0 and if y is less than height, or use cgrect contains point, but actually its implementation is written as those 4 conditional checks. But Swift 2.0, we can do this by matching the point to the ranges in the tuple. So it might look familiar for those of you who used case in switches. It's basically a case taken from a switch statement and put into an if statement. I have a comparison slide coming, so for those of you confused. But first of all, I want to talk a little bit about if case let where. Notice how the name gets longer in each slide. We can actually introduce the value binding in our if case statement. So, like, if case let where is for if case, what case let where is for case. So, too many prepositions. In this example, I think it's pretty clear. In this example, we bind the value x, then check whether the y value of point matches the 1 interval to int max, so from 1 to infinity, and then we check whether the x is less than 0. If so, the point is in the second quadrant, so in the top left of the coordinate space. So comparing this to the switch statement. So basically with if case let where, switch subject case pattern where condition becomes if case pattern equals subject where condition. One more thing, you don't have to write a default case where using if case. Asterisk there, multiple cases are not yet supported as of beta 3 of Swift 2.0, so you can't do if case pattern 1, comma pattern 2, and match for either of those patterns. You have to do one pattern for each if case statement. This raises a compiler error, but I think till October they will introduce multiple case statements. Okay, my last pattern matching example has the most random collection of English conjunctions and prepositions in the name, four case Latin where, and it's actually a value binding inside the case. It allows us to do a value binding inside the case statement inside the for in loop. So when evaluating the where clause here, we actually have the x and y bound for only those elements that are non-optional. Because let me remind you that optional is an enum with some or none cases in Swift. And by typing case.sum, we actually pick up only those values that are sum and then do the value binding. So there's a let x and y in there. And then evaluate the where clause. So as always, x and y are non-optional. There are no exclamation marks or question marks there. In this example, we just check whether the point is in the third quadrant. Comparing this to the classic for in loop, for element in subject, if case pattern equals element where condition just becomes if case pattern in subject where condition. Notice that the element part just vanished from the first example. Another asterisk, multiple cases are not yet supported inside the for case in loop. Okay, that's pattern matching. Now let's talk quickly about reflection capabilities in Swift. Imagine you have a vector type, another geometry structure in our app. It has a start point and an end point, and a computed property of length. Then we instantiate the vector from 0, 0 to 1, 1, and open up the result view in our playground. We see this. Okay, that is unreadable. We can't tell the difference whether the first one is the start point or the second one is the start point. It's just a couple of zeros and ones that we don't understand. So this is where reflection comes in. There are three methods of reflection in Swift. First of them is by using custom description. So everybody wrote a printable type in Swift, overrode the description or the bug description property. The second one is by specifying custom children tree. It's like overriding what Swift compiler sees as properties of your type. You can show the reflection mechanism that your type has another set of property that it actually has. You can override this behavior. And we may declare a custom quick look preview for rich audiovisual representation of your type. So the first one, obviously, many of you have implemented this. It was previously called printable in Swift 1.2. Now they changed its name to custom string convertible. And all you need to do is to override the description property and return some arbitrary string. In our case, that's the result of that. It's more readable. We can see the start point and the end point, but we actually still cannot see the length of our vector. And for debugging purposes, it may be actually quite important to us. So the second method is to override the children tree, so aka define a custom mirror for your type. In this example, we instantiate a mirror structure and then give it a dictionary of where the keys are your properties in your type and the values are the values of those properties. So in our case, we can define the start and the end point and actually print it. And then we can include our computed property, length, in this example. And that's the result in our playground. We can see the start point, the end point, and the length, which is square root of 2. Very correct. So the custom preview. This is the last thing you can do, and I think it's most ambitious thing you can do in when representing your types in Swift. It actually allows you to create a visual or audio-visual representation of your type. So things like sounds, links, attributed strings, rectangles, images, views. The Playground Quick Look enum has 18 cases. So there are cases for rectangles, sizes, points, views, everything. In our example, we can draw the vector by using UI Bezier path and return the Playground Quick Look.Bezier path enum with associated value. So we can see this. Of course, it's not complete. We can't see the start point and the end point, but as you may imagine, we can do it pretty easily by just adding those things, by just drawing those things inside the view. So, 3 basic reflection principles are: they override the textual, the children tree, and the audiovisual representation descriptions of your type, so that the Swift Playground and also LLDB, because these reflectables work not only in Playgrounds but of course in LLDB as well. And they are unfortunately still read-only, so there is no Objective-C like introspection in Swift yet. Okay, so for those of you Objective-C developers, the last thing I want to talk about today is a trick in Objective-C bridging. So, by now, there have been 3 bridging methods in Swift. Either you can inherit from an Objective-C class, so you can create a class that inherits from an object or UI view controller. You can use @Obj_C attribute to explicitly specify that your function or your class is available to Objective-C. And for importing Objective-C code to Swift, we can use bridging headers. And that's basically it. Or is it? We all know we can convert between array and NS array with no effort whatsoever. We don't have to do conditional typecasts. We just type S and as array, and it just works. You might be thinking that this is a hidden Clang or LLVM feature. No. It turns out there is a hidden protocol in Swift called _Objective-C bridgeable. And keep in mind that Swift hidden symbols are not undocumented private APIs. So because Swift binaries are binary compatible as Apple advertises it, submitting an app that uses this hidden standard library functions is not a case for rejection. And that's what, for example, Crashlytics did when demangling type names were before string 1.2. So the frameworks that shipped with Crashlytics that used a private Swift function didn't get rejected at Apple Review because Swift binaries ship with the app itself. So by using this type, you don't need to be afraid about rejections. Okay. Objective-C bridgeable protocol looks like this. It has a type alias for corresponding Objective-C type. It has 2 helper functions to get to know whether your type can be bridged to Objective-C. It has an instance function to bring a type to Objective-C, and 2 functions for bridging from Objective-C to Swift. One for conditional typecasts and one for force typecasts. So the second one, conditionally bridge, is used when you use S ? in Swift. So surprisingly, we are developing a geometry application, and we have an Objective-C native class that inherits from an object. It has 2 properties, $x, $y, and an initializer that creates an instance. But in Swift, we want to use a structure, thread safety, immutability, value semantics, yay. So why can't we use a point and XYZ point and in an interoperable way? So yes, we can, in just 25 or minus the white spaces, 20 lines of code. We create our, I hope it's readable, we create our Objective-C type in type alias, then some basic boilerplate codes such as return true, return Objective-C type self. Then the two most important functions, bridge to Objective-C, where we create an instance of our Objective-C corresponding class, and bridge from Objective-C, where we assigned, I don't know why this isn't a return type, but it's in out parameter, but we assigned the result parameter to our Swift corresponding type. And in the third method, I used this same thing as in the forced bridge from Objective-C, because in my case, the typecast always succeeds. There's no way these things cannot be interoperable by using points. But for example, when you try to implement it on generic structure or some enums with associated values, you will need to check whether the containing types can be represented in Objective-C, and maybe you may fail the conditionally bridging from Objective-C to Swift. That's why it's optional. So by implementing this protocol, everything on this slide works. So of course, the conditional S question mark typecast is working, but Objective-C point S point and Swift point S XYZ point work as well. There is no question mark, there is no exclamation mark, and you can even specify that your point is of XYZ point and use point, Swift point structure in the store point value in there as well. So yeah, a quick recap. In this evening I talked about literal convertibles, how you can use them to initialize your types from string literals. String interpolation, how you can control how your types appear when interpolating. Pattern matching, so I talked a little bit about more advanced pattern matching that was introduced in Swift 2.0, for example, for-case inletware. And I talked about reflection, so how you can audio-visually represent your types in playgrounds and LLDB. And I showed you a trick that allows you to impersonate an Apple engineer and create a true interoperable types in Swift and Objective-C. And last thing, how you can learn those things. So you can read Xcode release notes and find with every fixed issue there is a number in parentheses. This is a corresponding radar number. You can go to openradar.me, check if it exists, check what this radar was about, and maybe it was opened by airspeed velocity and it just blows your mind. Or speaking of airspeed velocity, you also may want to follow right people on Twitter. So these are people who also mine Swift standard library, such as, I don't know, Robert Bünke or airspeed velocity. You can study the Swift interface yourself. So that's how I found out some of those types. You can use LLDB type lookup. This is a feature for those of you who watch What's New in LLDB from this year's WWDC session. They know what I'm talking about. This is a new feature in LLDB that allows us to introspect the hidden Swift types in Swift standard library, and that's how I found out about Objective-C bridgeable. Most importantly, you must experiment in playgrounds, try new stuff, check if it compiles, check what results it produces. So, are there any questions? Okay, so thank you very much.